In order to actually evaluate inverse trigonometric functions, we're going to start with our known values from the unit circle diagram. Now, you've sine these two lines, the sine line and the cosine, for angles in the first quadrant. Tangent is just built as sine over cosine. And so that's where all these values come from down here. This u stands for undefined because we're dividing by 0, and that corresponds to hitting that vertical asymptote at pi over 2. Okay, so evaluating the inverse trig function. Basically, we're going to use this same table of values, but we're going to use it in the opposite direction. In the past, we would say, okay, we have an angle like pi over 4, and we want cosine of pi over 4. So we look at pi over 4, look at the cosine row. That's going to be square root of 2 over 2. Since we're doing an inverse function, we're going to do this backwards. You're going to be given a value. You're going to find it on the chart, and then you're going to use that to look up an angle. So for example, the inverse sine of square root of 3 over 2. So we're going to look at the sine row. We're going to look for 3 over 2, 3 over 2. The corresponding angle is pi over 3. Remember that the output of an inverse trig function will always be an angle. And so it's answering the question, what angle has the property that when we take the sine of it, we get square root of 3 over 2. And that's this one right here, pi over 3. Now this works for angles in the first quadrant. What if you have something that's not in the first quadrant? So for example, inverse cosine of negative square root of 2 over 2. Here's where we have to think about the picture a little bit. Going all the way back to our unit circle diagram, the inverse cosine of negative root 2 over 2. What are we looking at? We're looking at an x-coordinate because it's in cosine. We're looking at the x-coordinate is negative square root of 2 over 2. So this is x equals negative square root of 2 over 2. We want the angle that corresponds to that value. Now we have two values. We have one in the second quadrant, one in the third quadrant. And here's where we need to remember that the cosine has a domain from 0 to pi, 0 to pi over 2. Sorry, has a range from 0 to pi. And so we want the value in the second quadrant. The question is, what is this angle? And here's where we have to use our unit circle diagram, this chart, reference angles, the whole works. So when we reflect this back over here, what angle will we have? Well, this is going to be square root of 2 over 2. So we look it up, that's pi over 4. So the reference angle here is pi over 4. When we reflect that back over here, that reference angle is pi over 4, which means that the actual angle, going from here to here, is going to be pi minus that pi over 4, which happens to be 3 pi over 4. So a lot of this is really just playing with the geometry and thinking through the diagrams that we've been working with the entire semester. If you find this a little bit confusing, it's going to take some practice, but it's not that hard. You always want to be able to think about the unit circle diagram, draw the picture, think about whether you want the x-coordinate, if it's a cosine, the y-coordinate, and see what you can do by thinking through this picture, because this picture is really going to drive things forward. So what happens if you're asked to evaluate a function where it's not a known value? So for example, the inverse sine of 0.4. Well, there's not really much you can do other than put it into a calculator. There are some graphical methods where you draw the unit circle and you have a very fine grid and you can sort of estimate the angle based on that. But really we just throw this into a calculator. The thing to keep in mind is whether your calculator is in degree mode or in radians. Typically, we want to work in radians unless there's a specific reason to work in degrees. What are some of the reasons? Well, one reason we might be working in degrees is because we're doing a problem that has a practical application. Measurements, more often than not in real life, are done in degrees rather than radians. In math, we do it in radians because it makes all of our formulas nice or whatever, but most people are more familiar with degrees. So that would be the overriding reason to do it in degrees rather than radians. But basically, you just throw this into a calculator, you get some number out of it, and this is the best you can do. When we do this inverse functions, when we have a value in radians, you typically want to keep maybe 3 to 4 decimals because if you do more calculations later on, you'll create rounding errors if you don't keep enough decimals here.